In this video, we're going to focus on IR spectroscopy, specifically how to use it to identify functional groups in organic molecules. So let's compare the carboxylic acid with an alcohol. When you have a carboxylic acid, you're going to have a very strong, very broad OH stretch. This OH stretch, it shows up at a signal between 2500 and 3300 centimeters to the minus 1, which is a type of wave number. Now, the carboxylic acid also has a very strong CO stretch. And the CO stretch, it shows up at a signal of 1700 wave numbers. Now, you may want to write these numbers down because you'll need it in order to identify these functional groups in IR spectrums. Now, the alcohol, it only has the OH group. So it has a strong absorption around 3200 to 3600. So that's the OH stretch of the alcohol group. Now let's move on to our next two molecules, the aldehyde and the ketone functional groups. Both molecules contain the carbonyl functional group, and the CO stretch of these two functional groups is very similar to a carboxylic acid. It's around 1700. Now, the distinguishing feature between an aldehyde and a ketone is the CH stretch of the aldehyde. This signal here is the alkane CH stretch, which typically shows up for almost all organic molecules that has a CH functional group, and that's around 2900. So you'll see that for the ketone as well. But this part here, this identifies the aldehyde over the ketone. So the aldehyde will have a signal of around 2700 centimeters to the minus 1. So that is the aldehyde CH stretch. So that corresponds to that part of the aldehyde functional group. So that's how you can distinguish an aldehyde from a ketone, is the presence of this signal, the aldehyde CH stretch. Now let's compare the ester and the ether. The ester functional group has a carbonyl CO stretch of around 1700, very similar to aldehydes and ketones. The ether, it doesn't have the carbonyl CO stretch, but it does have a single bond CO stretch, and that is between 1000 and 1150. So something that you want to take into mind is that double bonds have higher wave numbers than single bonds. The C double bond O stretch absorbs at a higher energy than the CO stretch of an ether. And triple bonds have even higher wave numbers than double bonds. We'll talk more about that later in this video. For now, you want to take into account the type of carbon that is attached to the oxygen. That is, this is an sp3 carbon. Here, we have an sp2 carbon. So therefore, the CO stretch is going to be different. It's going to be higher. It's going to be between 1200 to 1300. And the reason for that is the resonance that can form here. So let's take this lone pair, let's form a pi bond, and let's break this pi bond. And now let's draw the resonance structure of the ester. And let's add the corresponding lone pairs. So we could see that the sp2 CO stretch of the ester has more double bond character than the sp3 CO stretch of the ether due to resonance. And why is that important? Well, as we've established, a double bond CO stretch has a higher wave number than a single bond CO stretch. So a CO stretch with more double bond character is going to have a higher wave number than the CO stretch with more single bond character. Now we do have an sp3 carbon attached to the ester. So therefore, we're going to have this signal as well for the ester on the left. We're going to have two CO stretch, an sp2 CO stretch and an sp3 CO stretch. But the ether, it only has the sp3 CO stretch. And so that's how you could distinguish between an ester and an ether. The first characteristic is the carbonyl functional group. That alone is enough to distinguish it. But the second thing is the presence of the sp2 CO stretch versus the sp3 CO stretch. Now let's talk about primary and secondary amines before we go into amides. Now the primary amine, which has two hydrogen atoms attached to the nitrogen atom, it will show up as a double peak with a signal somewhere between 3300 and 3500. Now the secondary amine only has one hydrogen atom attached to the nitrogen atom. And so it's going to have a single peak between 3300 and 3500. So that's how you could distinguish the amine, the primary amine, from a secondary amine. Now the amide, it does have the carbonyl functional group. And so we're going to have a CO stretch very close to 1700. And we also have the NH2 group, so we're going to get this signal as well, between 3300 and 3500. So to distinguish an amide from an amine, you need to look for the presence of the carbonyl functional group. And to distinguish a primary amine from a secondary amine, look for the double peak in the primary amine and a single peak in a secondary amine.